So I'll start with this material here, and I want to let's tackle quantum numbers all together, okay? Okay. There's a few different types of quantum number questions that could be asked. So let's go through all of the types that I at least will remember right now. There's a couple that I gave to you. Okay, here's one style. One style is to say, I'll give you an orbital, say 2D, and I'll ask you, is this allowed or not? So in order to do this type of problem, so the question is it allowed? Question mark. Okay, what you would do is you would find the quantum numbers that are given. So for example, n is what here? 2, L is D, which is what number? 2. If you forgot, L starts at 0, counts up, and it also has a letter going along with it. A lot of students forget this on the test and get the letters mixed up with the numbers, so I'd make a little table for yourself on the exam when you start. So you're not the one who gets that confused. Okay, is this okay? No, so this is not allowed. Okay, 2D. 3D would be okay, but 2D does not work. Okay, let's try another one. Of those, let's say you have 4D, and let's say m sub L equals -3. All right, so let's put in the quantum numbers that we know. What's n? 4 is the first number. L is D, which is, oh, it's right there, 2. And then m sub L is -3. Okay, do n and L work, first of all? Yeah, a 4D is completely possible. Okay, if L is 2, will m sub L be -3, ever? No, that can't happen. So there's another not allowed scenario. Let's go through what m sub L could have been. So L is 2, m sub L goes from -L, -2, up to +L, +2. So -2, -1, 0, +1, +2 are all allowed. Anything outside of those 5 numbers doesn't work. Okay, so that's one style of question. Another style of question would be, let's say you have n equals 3. And I want to write all the other possible quantum numbers. So for example, so they give you this, and you want the other numbers, other quantum numbers specifically. So let's start with L. If n is 3, what's the smallest number L could be? 0. Yeah. Can it be 1? Yes. Can it be 2? Yes. 3? No, so it can't be 3 because n and L can't be equal. Okay, so 0, 1, 2 are possible values for L. Now let's go m sub L. I'll write that down here. We're going to have values each dependent on which L value we're talking about. So let's start with L equals 0. If L is 0, then m sub L goes from -L, -0, to +0, which is just 0. Okay, so if L is 0, m sub L is 0. If L is 1, how many m sub L values will we get? 3. It'll be 0 and then plus or minus 1. So it goes from +L +1 to -L -1 and 0 in the middle. Okay, if L is 2, how many values of m sub L will we get? 5. 0 plus or minus 1 plus or minus 2. So it goes from +L +2 to -L -2. So it includes all those 5 digits. Okay. And then for all of these, so m sub s is the one that's not connected. It can be plus or minus a half. It's not mathematically connected to the other values, say like n and L are connected. So it's always just plus or minus a half. A variance, so those are all the other possible or allowable quantum numbers, if you were asked. A variant on this question, I'll put it in a different color, would be if n equals 3, how many electrons that are spin up would be allowed. So how many spin up electrons could you have in that scenario? So same situation, n equals 3, but now I want to count the total number of spin up electrons. Okay, in this case, see this m sub s value? This goes for every single digit here. Okay, so for example, let's start here. How many orbitals total are here? 5. I'll put that in parentheses down here. So that's the total number of digits. 0 plus 1 minus 1 plus 2 minus 2. 5 total digits. Here there's 3 total digits. And here's there's 1 total digit. Okay? So the total number of orbitals is how many? 5, 3, and 1. Sounds like 9. Okay, if there are 9 total orbitals, how many total electrons could I fit in there? I could fit 18. 9 times 2. 18 total. 9 are spin up and 9 are spin down. So to answer the question, that's how you get 18. So how many electrons are spin up? 9 are spin up. So, or means plus 1/2. 9 would be spin down, thus a total of 18. 2 electrons per orbital. That's another style of question. Let me see. Another style of question could be as follows. Let's say you have helium. No, let's make it a little harder. Let's do lithium. Okay. Oh, this is going to be comboed with electron configuration. The electron configuration of lithium is 1s2, 2s1. Right? Yeah. Okay. So a possible question here is to take this. We could take any electron here. How many total electrons would be here, by the way? 3. You would just count the superscripts, 2 here and 1 there, total of 3 electrons in lithium. Let's say I took this electron here and I wanted, what are all of this electron's quantum numbers? This is another way to ask a quantum number question. Okay, so if I did that, what's N? 2, what's L? It's S, which is 0. M sub L. If L is 0, M sub L is 0. And then M sub S. It's pretty arbitrary, but there's 1 electron, so you have to pick one of the spins. It could be the up spin or the down spin, really. Usually I start labeling up spins first, so, but a plus or a minus 1/2 would have been okay there, either one. I put plus 1/2, that means I thought it was the up spin, but that would have been arbitrary. Okay. Any questions on any of that action before I go to, I want to do electron configurations next, because we just kind of started it. Yes?
When we're writing the M sub L style, do we have to write 0 2 different times like we did, or could we just write it?
Oh, the question is for up here, when we're writing the M sub L values, do I need to write 0 each time? Yeah, because this 0 goes with that one, this 0 goes with that one, and this 0 goes with that one. So they are independent zeros, or they're associated with different L values. That, another way to say it is, well, that's fine. Okay, let's do some, oh yes?
If there was 4 electrons, would you still get to pick if it was plus or minus 1/2? Or?
If there's 4 electrons, well, there's 3 electrons here. I didn't do these 2. So you'd have 4 quantum numbers for every single electron. So there's 3 electrons here. Each electron should have its own 4 quantum numbers. Here, because there's 2 electrons, one's up spin, and thus by default the other one must be down spin. Okay? So yeah, that would be good practice to write the 4 quantum numbers for each of these 2 electrons. That could be a possible question as well. I just picked this one at random. Okay, let's do electron configurations. Somebody asked me, I think for the F quantum numbers, or the F electrons, I wouldn't really ask you that on the test because there's so many exceptions that kind of go there. So more likely what I would do is I would give you the electron configuration and have you work backwards. So let's try that. And I think, let's see if I have one. Let me see if I have one. And there's a really easy way to do it, and then there's an exceedingly hard way. So we'll do the exceedingly easy way. Oh, here we go. This is one I wanted. So we're doing quantum. Let's just do it down here. I got a lot of space. Let's say I gave you this configuration: xenon, 6s. Ooh, that was ugly. 6s2, and I want to do 4f11. 4f11. Let me give you a few moments. Head start on me. I'll give you 10 seconds. See if you can figure out what you think it is. Then I'll show you how I did it in case your method is different than mine. So going backwards, what element is that? It's a neutral element I'm looking for. Okay, if you're still working, you can keep on working. Here's how I do this. I start with the noble gas configuration, the xenon. I look at it, and it's atomic number 54, the smaller number. I'm going to write that down because if it's neutral, that's the number. This is the number of protons for xenon, but it's also the number of electrons if it's neutral. Then there's 2 electrons here, and then there's 11 here. I'll just add these numbers up and see what I get. Let's see. 54 plus 11 plus 2, what is it? Okay, I'll trust you. 67. Cool. And that is holmium. Hope. So some people try to do this by back calculating or basically kind of working backwards from the electron configuration. That's usually pretty hard because there's a lot of exceptions in the periodic table, and I just gave you one, so on purpose. So the much easier way is just to count up the total number of protons, which would equal the number of electrons for a neutral element. Yeah. Okay. Next, the configuration. Let's do drawing the orbitals and the nodes at the same time, because those all go together. And I put a star here. I forgot why, but I hope I do this question justice. Okay. Do you want me to pick like a medium level difficulty, hard one? Totally up to you. I don't care. Medium level difficulty? Okay. Let's go. I want you to draw a, oh no, let's make it harder. No, that's a good one. That's medium. 4PZ. Have we done this in class before? I'm just picking it at random. We have? Oh my gosh. Let's do a 4D x squared minus y squared. Have we done that in class? I don't think so. Okay. So what I do, if I have this, and I want to draw the orbital, and I want to draw all the nodes, that would be a pretty classic question. The other way to do it is if I draw it for you, and then you interpret it. Those are kind of the 2 styles. So if you're drawing it a little bit harder, first of all, let's get the quantum numbers down. So N is 4, L is, yeah, D, which is the number 2. Okay? So now I'm going to graph it. I'm going to graph it on the XY axis, because you can always tell that by the subscripts. So let's go. Here's going to be the y-axis. Here's going to be the x-axis. The dx squared minus y squared, or the squared ones, lie on the axis for the d orbitals. So that'll look something like this. It looks like a four-leaved flower, I suppose. They're all supposed to be symmetric looking. And it lies right on the axis. So there's the dx squared minus y squared. I've got it drawn. Let's draw the nodes. So let's calculate that. How many nodes do I have here? 3. And remember, it's n minus 1, or 4 minus 1 is 3. Okay. A d orbital is born with how many nodes? 2. Yeah, d orbital always has 2 nodes initially. They bisect the petals. So we got this node and this node. These nodes are called what? Angular. So the ones that are born to it or have initially come with it are called angular nodes. They're planar. So they lie within the plane, or they look flat or like a line the way I'm drawing it. Okay, there is a third node. What's the name of the third node? Radial. And for a radial node, whenever there's a third node that just doesn't come with it, and remember, a node means where there's a 0 probability of finding an electron. So electron probability lies within the lobes, or the distribution where you can most likely find the electron, are inside these little lobes there. So the third node, imagine drawing a circumscribed circle in here. Now you only need to draw the part that's inside the lobes, but I'm drawing the whole circle just so you can see it looks like a circle. And thus it's called radial. It has a radius to it. And so this one is the radial node. And there's the 3 nodes now labeled. Remember, the electron is not found at a node. Okay? This also has shading. Somebody mentioned that. I'm not grading it on the exam, but do you want me to draw it for fun? I don't know if McCurdy's grading it or not. I think he is. I'm grading it on the final. Okay, first, if this was a 3dx squared minus y squared, it would just like this. I shade. I think McCurdy puts pluses and minuses. Same idea. If there's a node, the shading switches at the node. Meaning, it would kind of look like this. But then at the node it switches. So if it was shaded, it goes to unshaded. And here if it was unshaded, it goes to shaded. So it switches its phase at the node. My students, I'm not going to grade this, so you can decide to do that if you want or not on exam 2. It's important for sure on the final. But what you don't want to do if you're my student is to do it wrong. Because then I would be forced to grade down. If that makes sense. Because you can't have something wrong. It's better to not do it if you're not sure. But that's what it would look like here. Okay. Questions on this drawing? So I did the nodes and I did the drawing the orbitals. Any other questions about drawings? Whoa. Okay. Yes. First up there.
For the radial node, on the test, can we either draw the whole circle or the part of the circle, or is there a specific thing?
No, you don't have to draw the whole circle. So you could have. I would typically be drawing. Okay, this is supposed to be symmetric looking again. I would just personally, I just draw this.
Can we do it either way, though?
Yeah, I mean, either way is fine with me. If that's what you're curious about. Yes. Do you want to, you're asking, should you do this? I guess so. I think it looks uglier, but if you want to, that's fine. Yeah. Yes.
For shading at the X and Y, does it matter where we're shading? Like, what if we put on the outside for Y, for the Y axis shading?
For the shading? Meaning if this was shaded?
Yeah, if that was shaded.
And this is unshaded?
Yeah.
Okay. The shading just is somewhat arbitrary at this point, and it's just showing a switch in the phase, more so than anything, yeah, that's all I'm really showing right now. So it's showing a switch in the phase. So you could have put this unshaded and that shaded. Is that what you're asking about, or is there more to it?
So it wouldn't matter whether Y or X axis has different, like, opposite shades. But let's say in this case, Y is shaded on the outside.
Yeah, if this was shaded here, then you have to switch everything. So shade, unshade, unshade, shade. And then unshade, shade, shade, unshade. That's fine. Okay. All right. Let's do a little Rydberg, and we'll do the wavelength issue. For Rydberg, and we'll do an example too. Let's first get the equation down. I'm not necessarily on my test, and I think the same for McCurdy. We're not necessarily putting all these equations together. So let me show you what I mean. You'll see this. I'll give you the Rydberg constant on the test, and then you'll see something like this, and then you'll see something like this. Okay? But for your purposes, it's kind of nice to put these equations together. So this energy equals h nu, and this energy also equals hc over lambda. So this is really on the top line the nice way to put it, but we're going to write all the equations separately. It's up to you to put them together if you want to. It's kind of nice because if you have a Rydberg equation, then you kind of stick stuff together. All right. So I need a volunteer to give me a number. 2 numbers. 7 and another number.
4.
A 4. Oh, too late. We're too slow. But I got the 7. Okay. So I heard the 7 first. So let's say we start at the 7 orbit and we're going to the 2nd orbit. Okay. First of all, am I putting energy in or taking it out to do that? In or out? Out. So when it drops in orbit, you're giving off energy in the form of light. Is that light visible? Sometimes. Sometimes not. Sometimes it's in some other part of the electromagnetic spectrum. It could be UV light or gamma ray or whatever. Okay, so this is emit energy. What sign do we use, positive or negative, for this? When it's lost, when it's going out of the atom. Negative. That'll be true for other things. Energy, negative energy means leaving the system. Positive means going in. Okay, so if you were to calculate the energy, you would just say delta E equals Rydberg constant 2.179 times 10, what was it, minus 18 I think, joules, 1 over the initial energy squared, 7 squared, 1 over the final energy squared. Just that, it's plug and chug. From this numerics, would I get a positive or negative answer? Yeah, it'd still be negative. That agrees with our conceptual understanding. That's good. If you needed to convert this to another unit, another variable, you could. You'd want to take the absolute value of the answer to make it positive. And then you could say the first formula there on the top right of the screen, h nu. H on the back of the test is 6.626 times 10 minus 34 joule seconds times nu. So you can solve for nu. Or you can solve for lambda in the upper right of the screen. It would be h, 6.626 times 10 to the minus 34 joule seconds times c, 2.9979 times 10 to the 8th meters per second, all over lambda. So I'll circle again all the variables you could possibly solve for. Change in energy, nu, or lambda. All those are solvable. It's really just plug and chug from there. Any questions on Rydberg? It should ultimately feel like a plug and chug sort of formula, or calculation, I should say. Okay. Sometimes we'll tack on to this, based on the wavelength or the frequency. You look on a little chart or a graph and you figure out what light was given off. Infrared, red, whatever. Yes? Sig figs. That's good. I think in all these formulas, how many sig figs would you have, anyone? 4. Yeah, 4 looks like the least amount of any of the numbers, so not exact numbers if that's what you're asking. Except for the 2 and the 7, those would be exact, but it's lost by the Rydberg constant. Yes? The delta E, should it be negative or positive for the answer? Delta E would be negative. Though really, if you write a positive, I personally wouldn't grade down for that. I don't think recurring, it's just telling you which direction the energy is flowing. So if we asked you, you know, if energy is, what's the energy that's emitted? By emitted, we mean a negative number. So I'm not personally a stickler to that, but you should ask your course instructor. But yes, you better have a positive number for these things, because then we think you're a little wacky if you put a negative number for either of those. Okay,